All right. Hi, everybody. Thank you for coming today to the Western Museum of Flight. As introduced, my name is William Whittenbury. I have a background in the space sector, so I interned at General Electric Aviation, and then I went to NASA Marshall Space Flight Center in Huntsville, Alabama, which is where I had my experience on Artemis, which we'll talk a little bit about. As I'm telling people today, this talk is about the rocket, not about me, but there will be a short section about what I did. After that, I went to my current company, which is Northrop Grumman, but I'm not speaking today as an official company representative. I'm just sharing my own personal experience. I also will have my master's degree in astronautical engineering in 10 days, so we're almost there. Thank you, almost there. Okay, so today we're going to be talking about the Artemis program and specifically the Space Launch System, which is the main rocket used for the Artemis program. So just because it's been in the news a lot lately, I feel like most people have heard of it, but up until a few years ago, it was kind of under the radar. So raise your hand if you have heard of the Artemis program before. Okay, good. This is a good audience. I figured you guys are here because you care and you want to know. But a lot of the general public still doesn't know that this is happening. So as I'm sure all of us are aware, in the 1960s and early 1970s, we landed on the moon with the Apollo program. And then we haven't been back to the moon since. And there's a few different reasons for that. It's actually not for lack of effort or for lack of desire on NASA's part. It's been due in large part to funding and political challenges, not technical issues. That is finally changing, and now we are going back this time to stay, which is very exciting. Another exciting angle to the Artemis program, which ties in very nicely with the new exhibit that we have across the way in the other hangar, is that Artemis is also seeking to be a more inclusive space exploration program. So we're doing this with international partners. We're going to land the first person of color on the moon, and we're also going to land the first woman on the moon. So very exciting program. And all of this is being enabled by what's called the SLS, or Space Launch System. So we'll talk a little bit about how that came about, and then specifically about the Artemis I mission, which was the first test flight, which occurred last November through December. So pretty recent, and then there's also some new information that's come out lately about Artemis II, which is the next mission that's happening next year, and so I'll share a little bit about that as well. So before I run into that, Apollo wasn't supposed to be the end. NASA had a very detailed plan for what they wanted to do after Apollo called the Space Transportation System Integrated Program Plan. And they published this whole big long paper about this. And the idea was to leverage the technology that they had developed for Apollo to create a sustainable presence on the moon, and then eventually extend that into Mars exploration by 1986. And this would have theoretically worked if funding had allowed. The idea was a multi-step system. They wanted to have a reusable space shuttle. They wanted to have a space station in low Earth orbit that this shuttle would go back and forth to, carrying cargo and passengers. Then there would be nuclear-powered space tugs, which would go from that low Earth orbit space station to the moon and back. And then eventually those would develop a permanent lunar surface base. And then eventually these nuclear shuttles would be bundled together to create the Mars vehicles. It was actually pretty well thought out. Nixon took one look at this and said, you can have one of those things. And so NASA ultimately chose to develop the space shuttle because that was considered the key first step in that overall mission architecture. So we're all familiar with the space shuttle. It had a fantastic career from 1981 through 2011, but it didn't really get us back to the moon. It was strictly a low Earth orbit system. Eventually, we did get the second part of that plan when we got the International Space Station. So we did get some of the original plan, but not all of it, and the lunar component of it kind of fell by the wayside. There were several major attempts that NASA made over the years to try to put together another moon program. And the most promising of them up until now was called Project Constellation. I'm not sure how many people remember this, but Project Constellation was a big push under the second Bush administration, starting in 2004, to try to put together a new moon program. And at the time, it was called Apollo on steroids, was the idea. And the goal was to try to leverage the technology that already existed from the space shuttle program to create new heavy lift launch vehicles that would enable this new mission. And so there were two vehicles in this family called Ares 1 and Ares 5. They chose the name Ares because that was the Greek equivalent of Mars, and the eventual goal was to get people to Mars, not just to the moon. And that's why, if you see in the upper right-hand corner, the Constellation mission patch has the 3 crescents that was supposed to be Earth, the moon, and then Mars. So this was a big effort. They actually got pretty far with it. You can see that the left-hand rocket is the Ares I. That was the crew vehicle, and that was supposed to get the astronauts up to low Earth orbit, where they would then rendezvous with the Ares V, the bigger one, which had what was called the Earth departure stage, and it would also carry the lander. And they did a lot of development work on these based on the shuttle, as I mentioned. So you'll see these solid rocket boosters that are on these two vehicles. Those are derived from the solid rocket boosters used for the space shuttle with an extra segment, so they're slightly more powerful. And then to get people to the moon relatively comfortably, there was a capsule design called Orion, which you can see on the upper right-hand corner of the slide. That was going to be launched on Ares I, and that was essentially an expanded version of Apollo. It was a new design, but it was similar in overall concept to Apollo. Larger inside, could carry between 4 and 7 passengers instead of 3, and most importantly, it has a private bathroom. So this was a cool idea. They got pretty far with it. They actually test launched the Ares I. This was called the Ares 1X mission. This launched in 2009. It only tested the first stage. So the upper stage of this rocket was a dummy. The upper stage, which you can see was kind of the wider part of the rocket on the Ares I, was supposed to have what was called a J2X engine, and that was a uprated and kind of redesigned version of the J2 that was used for Apollo, a hydrogen-powered engine. But that was never fully developed, and so this test mission didn't launch a live second stage. But this, proved the concept. But around that time, 2009, 2010 timeframe, Constellation was running into some trouble. There were a few issues. It was behind schedule. It was over budget. We had the Great Recession happening at the same time. There were some technical problems. So the Ares I had a pogo oscillation issue, and that's where the thrust profile causes the rocket to kind of do this, and that's very uncomfortable for the astronauts inside, to put it mildly. They did eventually resolve that with a complicated system of dampers, but it was a very complicated solution to the problem, and it was kind of too little too late for this particular program. Interestingly, I have heard that that design has since been used for earthquake-proofing buildings, so it wasn't a complete waste. And then the Ares V, which was the larger rocket, had not really begun in terms of the development effort. They had the overall concept, but the detailed design phase had not happened yet. So eventually in 2009, a group of industry experts got together called the Augustine Commission. And the Augustine Commission looked very carefully at this program and what was going on with it and the overall environment of the time and the funding. And they finally decided, this isn't working. We got to do something else. And so in 2010, excuse me, the presidential administration of the day, the Obama administration, decided to cancel the Constellation program. And they had some valid reasons for doing this, but it left NASA kind of in the lurch. There were a lot of issues associated with this because Constellation had two purposes. It was not just to go to the moon, but it was also to replace the space shuttle for carrying crews to the International Space Station. They would go up on the Ares I rocket for that. So suddenly, the shuttle was about to retire, and as we know, the shuttle retired in 2011, and there wasn't a replacement for it. So that was a big issue. What ended up happening was NASA had to rely for several years on the Russian Soyuz vehicle to get people to the ISS for geopolitical reasons that I'm sure we're all very aware of. There were some issues associated with that. And so eventually, they had to figure out what to do now that Constellation had been canceled. The thing is that the story wasn't totally over. So a group of senators from both parties, so it was a bipartisan effort, in 2010 and 2011 got together and they said, this is a problem. We don't have a national heavy lift space launch capability. We were going to have it with Constellation, but now that's gone. And we also are about to retire the shuttle. We don't have anything to backfill it. We got to do something about this. And so basically, the Senate overrode the administration's decision to a degree. So Constellation was still canceled, but aspects of the program were salvaged. So the Orion capsule, which was actually fairly far along, was saved. And then the 5-segment booster design, which they had already proven on the Ares 1X test mission, was also salvaged. And they decided to put together a new program. And so the Senate mandated that NASA develop a heavy lift launch vehicle using this equipment and also making maximum use of space shuttle hardware. The idea being that they could keep the production lines open that were still in existence for the shuttle program, the skilled workforce was already in place, and all of those components were already human rated. And for those of you who are not in the space industry, the process of rating a component for human spaceflight is an expensive and time-consuming endeavor. And so the fact that all the shuttle stuff was already human rated meant that they could save a lot of time and money by reusing it. And so the idea was basically, how can we reassemble the stuff that we already have from the shuttle to make a new heavy lift rocket that will essentially save our moon program and also kind of keep NASA in the human spaceflight business. The second piece of this, which I won't cover in detail today, is the Commercial Crew Program, which was started to replace the ISS launch capability. And eventually that was contracted out to Boeing and SpaceX. SpaceX has been flying their Crew Dragon vehicle to the ISS since 2020. And then the Boeing Starliner is supposed to fly sometime soon. And there's been a few delays, but that's happening. So those were the two pieces of the puzzle to resolve this issue with retiring the shuttle and not having the replacement. So it wasn't, basically the bottom line is Constellation was not a total loss. They were able to get some stuff together from it. And the result of all of this was a new rocket called the Space Launch System, which, as I tell everybody, is a really catchy title for a moon rocket. Because the Senate essentially mandated it, the nickname immediately sprung out that it was the Senate Launch System. That has kind of stuck around a little bit, but you know, it's kind of fair because they did essentially force it to happen. But the SLS, as I'm going to call it from now on, has a number of improvements over the Ares design that makes it a lot more viable. The big thing is that the core stage, which you can see is the big orange section, is the same diameter as the Space Shuttle external tank. So if you guys remember, the Space Shuttle had that big orange tank. I'll show you a slide later that kind of shows some of the technology heritage. But basically, they stretched it, kept the same diameter so they could use the same tooling, and that became the core stage of the SLS. And then there are 4 RS-25 engines. These are hydrogen-powered rocket engines, the same as what's better known as the Space Shuttle main engine, so that's more of that Space Shuttle hardware. On the bottom of the core stage, there's 2 of those 5-segment boosters that were designed for Constellation, and that forms the first stage of the rocket. When you add all of that up, it has 8.8 million pounds of thrust, which is more than the Saturn V from Apollo and more than the shuttle. That makes it the most powerful operational launch vehicle today. There are some vehicles in development that might end up being more powerful, but they're not fully operational yet. And so it claimed an important place in history with that. The second stage, which I'll talk about in more detail later, is called the ICPS, or Interim Cryogenic Propulsion Stage. That is shared with the Delta IV Heavy rocket produced by United Launch Alliance, and so that's also already flight proven. And then above that is the Orion capsule with its service module. This is a multi-company, multinational effort. So the solid rocket boosters are manufactured by Northrop Grumman. Originally, Orbital ATK got that contract, and then they were purchased by Northrop back in 2018. The core stage prime contractor is Boeing. The engines come from Aerojet Rocketdyne on both the first and the second stage. The upper stage is from United Launch Alliance, which, as some of you probably already know, is a joint venture between Lockheed and Boeing. The service module actually comes from the European Space Agency. It is based off of their design for the automated transfer vehicle to the ISS. And then the capsule, the Orion, comes from Lockheed Martin. The escape motor comes from Aerojet Rocketdyne and Northrop Grumman. We did I think the jettison motor. No, so we did the main motor and they did the jettison motor. And then there's other smaller pieces that come from different companies. But as you can see, this is a major effort involving kind of a nationwide consortium of contractors. So here are some statistics. As I mentioned, 8.8 million pounds of thrust, which is 1.3 million more than the Saturn V. The payload to low Earth orbit is 95,000 kilograms. The next most powerful rocket that's currently operational is the Falcon Heavy. I believe these numbers are for the expendable configuration. The Falcon Heavy is 31,200 kilograms less to low Earth orbit than SLS. So SLS is a major jump in capability over what we currently have. The height is 321 feet. That is less than the Saturn V. So the Saturn V was 363 feet. So SLS is shorter but fatter, essentially. Core stage diameter 8.4 meters, which is 27 feet. So if you can imagine a 27-foot cylinder, that's pretty big. And what I think is kind of wild is there's 1,100 contractors. So I mentioned this was a nationwide effort. They got everybody involved. And the Artemis program overall, so that's not just the SLS, that's also the other pieces of it, supports 69,000 jobs across the United States in all 50 states and Puerto Rico. So this is definitely a major effort to try to bring the whole country in on this. And SLS was designed from the beginning to be human-rated, so it is, we think, about 10 times safer than the Space Shuttle statistically for a variety of reasons, mostly that it does have a launch abort system, which the Space Shuttle did not have. So I mentioned there's some shuttle flight heritage. You can kind of see here a little bit more graphically what's going on. So the orange tank that was on the Space Shuttle became the core stage for the SLS, stretched slightly, but same diameter. The boosters are almost the same, except they're a little bit longer on SLS. They have that extra segment, but they're reassembled from existing Space Shuttle hardware for the first 8 SLS launches. So they are literally pulling them out of the shed and using them again. And then the engines on the core stage are also literally pulled off of the orbiters. So the Artemis I launch this past November, 3 of the engines came from Atlantis. I forget where the 4th one came from, but they all had flight heritage on the shuttles. And so for the first 4 SLS launches, they are reusing existing shuttle engines. After that, Aerojet is restarting production of new engines in Canoga Park, so not too far from here. And the RS-25A engine is going to have a lot more 3D printed pieces and fewer parts overall and a lot of other advances. So I mentioned a little bit about the boosters. Here's a little bit more about them. So you can see there's a lot going on in this infographic, but I'll tell you kind of the highlights. So there's 5 segments, as I mentioned. And the reason why they have to be in segments is because these are made in Utah, and then they are shipped on rail cars to Florida, where they're assembled into the final product. And so basically the size of the segment, including the diameter, is dictated by what can fit on the train. And what can fit on the train is dictated by the lowest rail bridge between Utah and Florida. So it's kind of funny to think all these really advanced space launch vehicles are based on centuries-old infrastructure. And the running joke is that the rail gauge, which also helps determine this, is actually based on the width of a horse's derriere, because the Romans based their roads off of a chariot, which was based off of that. And so if you kind of trace it all the way through, that's what dictated the size of the boosters. But each booster puts out 3.6 million pounds of thrust. That makes it the most powerful rocket motor ever produced. Each of these boosters is more powerful than 2 of SpaceX Falcon 9 rockets combined. So very powerful motors. And like I said, they're reused from the shuttle. So there's a lot of hardware reuse, which saves a lot of money and qualification. Core stage, here's some more information about that. So the core stage also kind of has 5 pieces. The engine section at the back is the most complicated. That's where all the plumbing goes. That's where the 4 engines slot into. That white portion is called the boat tail on the back, and that's where all the engines come in. The hydrogen tank is the lower one. So the hydrogen tank is larger, even though the amount of hydrogen is less by weight than the amount of oxygen. Because hydrogen is not dense, it requires a much larger tank. And so the hydrogen tank is the largest individual piece of the core stage. That's on the bottom. Above that is what's called the inner tank. That's a structural support member, essentially, that kind of ties everything together. And that's also where the solid rocket boosters will bolt onto and attach. And so that section has to be stronger than the rest of the structure. Above that, kind of further to the right, is the oxygen tank. So that actually, by mass, is about 6 times as much as the hydrogen tank. But because oxygen is so much denser, and these are both liquid hydrogen and liquid oxygen, to be clear, it's a much smaller tank overall. And then above that is what's called the forward skirt, and that includes a lot of instrumentation as well as the final attachment up to the next portion of the rocket. So the core stage itself is 212 feet tall, which is huge. Up until the prototype Starship vehicle, which tried to launch in April, this was the largest rocket stage ever built. And it is the largest operational rocket stage ever built. So it is taller than any of the stages of the Saturn V individually. And interestingly, unlike the Saturn V, which had that 3-stage structure, this takes everything almost all the way up to orbit. And so this core stage fires for about 10 minutes over the course of the flight, which is a lot longer than a lot of rocket stages. And by the time it burns up, or sorry, by the time it burns out, it's almost all the way around the world. So when Artemis I launched, it launched from Florida. By the time the core stage burned out, it was over Hawaii. So that kind of tells you something, and that's going the long way. So that's, kind of tells you something about how far this goes and how fast it goes. And it also kind of explains why the core stage can't easily be recovered for reuse. That's one of the limitations of the SLS program, is that the SLS design is not reusable. But this is the overall information about the core stage. Very impressive. Overall, it has about 2 million pounds of thrust coming from those RS-25 engines. Speaking of the RS-25, this is the former Space Shuttle main engine, now the SLS main engine, produced by Aerojet Rocketdyne. That's kind of our local homegrown part of Artemis. So these are made in Canoga Park here in Los Angeles, and then shipped across the country for test firing and eventual fitting to the rocket. These have about 450,000 pounds of thrust each. They can throttle up a little bit beyond that. So for the RS-25A, which is the uprated version for future Artemis launches, they're giving them the ability to throttle up to, I think, 113% of rated thrust, so a little bit beyond what they are really nominally supposed to do. And although this is old technology, this was developed for the shuttle back in the 70s, it is still the most efficient large rocket engine currently available. And the reason for that is because liquid hydrogen has the highest inherent ISP, or specific impulse, of any rocket fuel because of the low mass of the individual hydrogen atoms. And the other reason why this is very efficient is it has what's called a staged combustion cycle. And so that means that basically all of the propellant ends up actually getting used, and none of it is lost in the process of cooling the engine like it is on some of the other types of engine cycles that are out there. So this is still a great choice for SLS, even though it's relatively old technology. Mentioned a little bit about the ICPS before. So ICPS stands for Interim Cryogenic Propulsion Stage. This was the upper stage of the Delta IV Heavy rocket, as I mentioned before, which has been flying for a number of years. In fact, actually, the last two are about to launch. So Delta IV is almost done. But they decided to reuse this upper stage for the first few SLSs, and that's why it's called interim, because it's only going to be used on the first three. And I'll explain later about what's coming next after that. But it has a single RL-10 engine. So the RL-10 is another hydrogen-powered engine that's been used in upper stages of rockets since the 60s. So it was originally brought in on the Centaur upper stage, which has been used on the Atlas program, as well as several other launch vehicles. And it has a really long flight heritage. I think it has something like 600 successful missions under its belt with no major failures. So it's an extremely reliable rocket engine, also very efficient and a good choice for the upper stage. But you can see on the left is the SLS ICPS. On the right is the Delta IV upper stage, and they're almost identical. Like, you can't really tell them apart except for the paint scheme. They did do some work to get ICPS human rated, so there were some internal changes to that you can't really see. I mentioned this was a national effort, so these are the major contractors for SLS, not all of them, but the major ones, and you can see that they are spread all across the country. There are reasons for this, mostly relating to the fact that NASA's funding relies on votes from senators. And if you can get your mission to have jobs in all the states, then you get the votes. So that's one of the reasons why they did that, but also it helps provide jobs, it helps enhance the US industrial base, it provides high quality education opportunities for people. I really see it as a win-win. It has been criticized as a jobs program, but if you have a jobs program that puts people on the moon, that seems like a good deal to me. A little bit more about Orion. So this is what we're launching on the SLS. This is an exploded view provided by Aerojet Rocketdyne, which has produced portions of this. Interestingly, the engine for the service module, which you can't see very well in this picture because it's covered up by that folded up solar panel, but you can see it on the lower right version, is actually the same engine as the Space Shuttle Orbital Maneuvering System engine. So those were those two smaller ones that were up on the top of the Space Shuttle above the three main engines. Same engine, again, pulled off the Space Shuttle. So they basically said, what can we get from the shuttle that we can use? And that engine also has heritage going all the way back to what's called the SPS engine, or the Service Module Propulsion System for Apollo. So it's actually kind of the same engine that they used on Apollo, which is cool. There's a major difference between Orion and Apollo is that Apollo used fuel cells for its onboard power, whereas Orion uses solar panels. The long-running joke of the enthusiasts of a certain franchise in the program is that Orion is the real-life X-Wing, because it has the 4 solar panels. And overall, Orion is a much more capable, more comfortable, more advanced vehicle than Apollo was. It can carry more people for a longer duration. It has more room inside, better computing capabilities. So the bottom line is it looks very similar, but it is greatly improved overall over what we were able to do before. A little bit about how much all of this costs. So SLS has come under some criticism over the years for the overall cost of the program, but I think a comparison between it and Apollo can kind of shed some additional context on that. So the development of the Saturn V, the rocket used for Apollo, in 2022 dollars cost a total of $51.8 billion. SLS development cost was $23 billion, so less than half of what it cost to develop the Saturn V. It took a little bit longer, 8 years versus 6 years, and that's because the funding was divvied out in a trickle. If they had really gone full force on it like they had with Apollo, it would have been done faster. You have to remember, Apollo was basically a national crash priority, whereas SLS has been kind of metered out over time. And sort of a gauge of that is that the peak NASA budget in 1966 during the Apollo program was 4.4% of federal spending for the year nationwide. That's the whole agency, not just Apollo, but most of that was going to Apollo. For Artemis, the peak NASA budget during the program period was 2021, and that year it was 0.3% of the federal budget. So not getting the same level of budgetary support that Apollo was getting, and still managed to develop the vehicle in a reasonable, relatively amount of time and for less overall cost. What's next for the SLS? There's going to be some improved versions of it. So we're going to have what's called the evolved versions, and the first of those is called the Block 1B. You can see there's a bunch of different versions here, but I'll give you some more details on the Block 1B. The Block 1B is going to be used for the 4th mission and beyond. And so it has a new stage called the EUS, or Exploration Upper Stage, which is basically a larger version of the ICPS that you guys already saw. And the first of these Block 1B vehicles is already under construction. And the key new capability here is that it's going to be able to carry a lot more payload, and it will also be able to carry what's called co-manifested payload. So not just the Orion, but something else below the Orion as well. A little bit more about the EUS. So you can see the ICPS is on the left, the EUS is on the right. It is significantly larger, and it will enable 40% more payload to the moon. So that's a pretty good deal. The main difference here is it has 4 of those RL-10 engines instead of 1. So it's just a much larger version of the same concept. The first weld test article for this is already under construction for the EUS. After that, there's going to be a vehicle called Block 2, which is still kind of in the early stages of development. And the main change for Block 2 is that there's going to be new boosters. The idea is that this will come into play after the 8th flight, because after that, the existing inventory of shuttle solid rocket boosters will be exhausted, and they'll have to start making new ones. And so when they make new ones, Northrop Grumman, which is the prime contractor on the boosters, is coming up with an improved version, which has a number of changes, which I won't go into a ton of detail on, but I think they're talking about a composite casing and some other changes that will overall make them lighter and more powerful, which will boost the payload capability even further. And so eventually the Block 2 version is projected to be able to deliver 130 metric tons of payload to low Earth orbit compared to 95 for the Block 1. So it's an overall improvement. So now we'll run through quickly the process for how this is actually built. So this begins with a process called friction stir welding. So all the individual pieces are welded together using this method at what's called the Michoud Assembly Facility in New Orleans. That's the same factory where the Saturn V was built, as well as the Space Shuttle external tank. They use this huge vertical welding fixture, which you can see on the left. And on the bottom right, you can see how big it is inside. Those are people working on the little joints. So that's how large the tank is. And friction stir welding is interesting because it uses this bit to essentially force the two pieces together without actually melting anything. They just kind of fuse together. It's really wild to watch. After that, what's called the TPS is applied. That's the foam. So you remember the Space Shuttle external tank had that orange foam on it. Same foam is going on the SLS. And the reason why we need that is because the cryogenic fuels, liquid oxygen and the liquid hydrogen, have to be kept really cold. And so we need that insulation. It's basically almost like a big thermos bottle. So that gets sprayed on. Then we have the tank join. Well, first is what's called the forward join. So they use this vertical fixture, which you can see on the upper picture, to put together the forward skirt, the oxygen tank, and then the inner tank. And then the tank join happens horizontally. They put the hydrogen tank on. And then they recently just changed up the process. Now, instead of doing the whole thing in New Orleans, now that part gets put on a barge and sent to Florida, to Kennedy Space Center, where they put the engine section on, which is the next picture here. That's the engine section join, so that's going on the back. After that, we put on the engines, so those get installed one by one. And then once that was accomplished, it was time for the rollout. So they rolled out the core stage from, at the time, Michoud. So for the first SLS, they did everything there. They've now changed up the process, as I mentioned. They made a big deal out of this rollout. They had a high school brass band show up to do a little performance for it as it came out. And then it went on this ship, the Pegasus barge, which you can see on the left, and that navigated it through the river system to get it down to first Stennis Space Center for testing, and then Kennedy Space Center in Florida. At the same time, an earlier test article was being used for what's called dynamic testing. And so this was basically trying to crush it like a tin can on purpose to see how much force that would actually require and making sure it could stand up to the launch loads. And the good news is it could. It did actually burst, but that was on purpose. And it showed that it had the required margin of safety for the mission. While this was going on, they started stacking the boosters. So Northrop delivered the boosters actually fairly early on, the individual segments. They had a long shelf life, so they could actually stay in the VAB, the Vehicle Assembly Building, Florida for a long time. This was the process for stacking the individual segments. You can see here, this is how they all came together inside the VAB, and those are all the work platforms. While this was going on, they did what was called the Green Run test at Stennis Space Center, which is in Mississippi. And they put it down there because it's in an area that doesn't have anybody else around it, and so when they test fire the rocket engines, it doesn't bother anybody. They had to do this because when they did this back in Huntsville during the Apollo program, the Saturn V test fire blew out all the windows in the shopping mall. And people didn't like that, and so they had to build a new center. So this is a picture from the first test fire of the SLS. They also did what's called a gimbal test. So these engines can what's called gimbaling, which is basically moving back and forward to change the direction of the thrust. It's called thrust vectoring, and that enables the rocket to control its trajectory. There were a whole bunch of different things that they were trying to verify with the Green Run. I won't go through all of them right now, but this is what they were trying to do, improve, and it did pass the test. Once that was done, the core stage was shipped back to Florida, and they finally stacked it with the rest of the rocket. So they dropped it down in between the two already stacked boosters. This is inside the VAB, the Vehicle Assembly Building, which is the largest single room in the world. It's large enough that it actually forms weather patterns inside the building. After that, the ICPS went on top, and then after several other individual steps, which I won't detail here, they put on the Orion capsule as the last step of the stacking. And finally, we have a moon rocket, which was pretty exciting. So for those of us who worked on the program, this was a big moment because we'd all seen the CG, computer-generated illustration of the SLS for years and years and years, and finally it was an actual photograph. So that was pretty cool. After that, they rolled it out to the pad with another brass band, and I think they brought in Yo-Yo Ma this time too. They really went all out. So they took it out there for what was called the wet dress rehearsal, and so that was basically getting all the way up to actually launching it without actually launching it. And so they had to make sure they could fill the tanks properly and all of that. That took a couple of tries because there were some first-time issues with it that they had to sort through, but eventually they got it to work. And then it was on the pad. So this is kind of a cool picture to me because it shows that 50 years after Apollo 17, which was the last crewed Apollo mission to the moon, which you can see on the left-hand side, we were ready to go back once again. So, and you can see it's a pretty similar setup overall. You know, not a lot has actually changed in the last 50 years. So my dear family humored me, and we all went out to Florida to try to watch the launch with a close friend of mine. And so I did get this picture of it on the pad, which was pretty exciting. And then the morning of the launch, we went out and camped out with 500,000 of our closest friends on the beach trying to watch it happen. And we slept in the car overnight and got there, I think, at 1 in the morning to try to get our spot. And we were all ready to go. And then half an hour before it was supposed to go, it was scrubbed. But we at least got the picture. There were a few false starts with this launch, so there were a few different issues. There was an issue with the engine bleed. That's what caused the first one to get scrubbed, and it turned out that it actually wasn't a real problem. It was a sensor fault, but you know, you got to be careful. The next one, there was a hydrogen fuel leak, which that's not good, so they had to make sure that was working. There were a few other issues kind of going at the same time. The flight termination system waiver was an issue. It was expired, and they had to get that recertified. And then they did this thing called the tanking test on September 21st of last year. That worked. And so they went, okay, we're finally ready to go. And then we had a hurricane. So they had to roll it back to the VAB to avoid the hurricane. They then rolled back out to the VAB in November. And they said, okay, we're ready to go on November 14th. And then we had another hurricane. And nobody was expecting this because we hadn't had a hurricane make landfall in the mainland US in November in 40 years. And so everyone at the time was like, are you kidding? But they actually decided that this particular hurricane was not powerful enough to pose a risk to the rocket, so they actually left it on the pad, which had me very nervous. But apparently it was fine, and so finally they launched it on November 16th, 2022 at 1:47 a.m. Originally NASA was trying to push for a daytime launch, but finally they just said, you know what, if it's going to work, let's just go. You know, this is a picture of it on the pad during the hurricane, so you can see we were all like, okay. But it was all right. And then here's some cool launch pictures. So the morning of, that was its last sunrise on Earth, which was kind of exciting, and then it took off. So here's the launch. Here's a picture kind of zoomed in. You can see the solid rocket boosters have by far the most dramatic flames, and the hydrogen engines on the core stage, you can barely see the exhaust because it's that clear blue color. This is a picture of the separation of the Orion from the ICPS upper stage, and then it was on its way. So here's the overall trajectory of the mission. So I will make clear, I think everybody knows this, but nobody was actually on the Artemis I mission. It was an uncrewed test flight, the idea being to test out the system. But it essentially replicated something similar to the Apollo 8 mission profile. It went around the moon and back, but it actually did enter what was called a distant retrograde orbit around the moon for a few days. So the overall timeline of this mission was such that NASA was able to verify everything that they wanted to on this vehicle, and then some. So some additional sort of bonus test parameters were verified. This is a super cool picture. So somebody had the bright idea of putting a selfie camera on the end of the solar panel on the Orion. Whoever thought of that was a genius. And we got all these great pictures. So you can see this is the far side of the moon that we don't normally see, and then the Earth beyond it. And that shows just how far out this mission went. Everything worked perfectly. So after all of the drama involving the scrubs and stuff, everybody was very nervous. But apparently the SLS performed so well that they said it basically looked like a simulation. They couldn't tell the difference between the actual mission versus the projections. And also Orion performed perfectly as well. It came back, it splashed down successfully. It was picked up by the USS Portland, which is a dock landing ship, and then taken back for post-mission evaluation. A little bit of stats about this. It was in space for 25 days, 10 hours, and 53 minutes, and it did beat the Apollo 13 record for maximum distance traveled from the Earth by a human-rated spacecraft. So pretty exciting. A shout out here to Charlie Blackwell Thompson. She was NASA's first female flight director, and she was the flight director for the mission, so she did a great job. Another shout out is these guys, the Red Crew. So right before the mission was about to launch, they realized there was a leak. And these three guys, Billy Cairns, Chad Garrett, and Trent Annis, went out to the pad and fixed it with the rocket fully fueled right next to them. So you can kind of see that picture in the lower right of them like wrenching on it and stuff. So these guys are super brave, and they got a lot of kudos for saving the mission. A little bit about what I did on this. I was in the Vehicle Integration Office, and our job was to put together what are called ICDs, or Interface Control Drawings, that control all of the different locations of the physical, electrical, and chemical interfaces between the flight side and the ground side of the system. And so I worked on what's called, this is a mouthful, the Liquid Hydrogen Tail Service Mast Umbilical Plate, or TSMU. And that's what you can see here, where the tower has that projection going onto the rocket. The interface between those two is what I prepared the drawing for. So that was my contribution as the intern. I was there for 5 months, but it was a very exciting time. This is a picture of me and some of the other interns at the Michoud assembly facility with one of the weld fixtures, and at the Stennis Space Center with one of the RS-25 engines that's used on SLS on Artemis I. I think this is one of the Artemis I engines. So that was pretty exciting. We got a few exciting things coming up. So sort of the last portion of the talk here is what's next. So Artemis II is happening. NASA recently announced the crew for Artemis II. And these are our intrepid explorers. So on the bottom, we have Reed Wiseman. He is the mission commander. He previously flew to the ISS. Above him, we have Victor Glover, who is also a veteran of the ISS. He was actually the first black person to serve in a long-term capacity on the ISS as opposed to just visiting. On the right, we have Jeremy Hansen, who is a Canadian astronaut. He has not actually been to space yet, but he served in the Canadian Air Force flying CF-18s. He will be the first non-American to go to the moon, so that's kind of exciting. And then on the left, we have Christina Koch, who is going to be the first woman to fly to the moon. She currently holds the record for the longest single space flight by a woman. She was in space for 328 days on the ISS. And she also previously worked for NOAA, and she also worked at the Antarctica Research Station. So she's been literally everywhere. This is the mission profile for Artemis II. Similar overall in concept to Artemis I, except there will be people on board. And that's due to launch currently in November 2024. That could slip because these missions tend to do that, so stay tuned. But there's a lot of other stuff going on too. So the Artemis II core stage, which will launch that mission, is almost done. They're just putting the engines on right now, so that's in that final stage of completion. The Artemis III core stage, they've made all of those 5 pieces. They're now working on starting to put them together. The Gateway station, which I'll mention in a minute, is under construction as well. The Artemis IV core stage is in initial manufacturing. So the bottom line here is that SLS has entered mass production, which means we're making about 1 a year. But that's, mass production. And then they've also put out the contracts for HLS, which I'll mention in a second. This is the Artemis II core stage. So as you can see, it's almost done. Pretty exciting. This is a lot of major news lately too. So HLS is the human landing system. This is what will be used to actually put people on the moon, starting with the Artemis III mission. I'm not going to go into a lot of detail on these because that's kind of outside the scope of this talk, but 2 providers have been selected. On the left, we have SpaceX with a variant of the Starship vehicle, which is so large that they actually need an elevator to get down to the moon, which is kind of interesting. And then on the right-hand side is the Blue Origin national team, which I think sounds like a real estate agency, but it has Blue Origin, Lockheed Martin, Boeing, Honeybee, Astrobotic, Draper Laboratories, and several other collaborators work together on this. Totally different design. So you can see 2 very different approaches to the same problem. The Blue Origin design was literally just unveiled like a couple of weeks ago, so we don't have all of the details, but the crew cabin is at the bottom, so they can basically step right out onto the lunar surface. So different concept overall. Neither of these are slated to launch on SLS. SpaceX will launch it on their own Starship vehicle, and Blue Origin will launch on their own New Glenn vehicle. Neither of those vehicles have reached orbit yet, so we'll see how the timelines on those go. And then spacesuits, Axiom Space and Collins Aerospace have received contracts for the spacesuits. Axiom Space is doing what are called the EVA suits, so when they're actually walking around on the surface of the moon, whereas Collins, although I think the picture is kind of a misnomer, is going to be doing the suits for when they're inside the vehicle. Gateway Station is without going into a ton of detail here, is a small space station that's going to be in lunar orbit, what's called a near rectilinear halo orbit. And this is basically a base camp for the mission. So the landers will go back and forth from this station. It's going to gradually grow over time. The first 2 modules are what's called the HALO, the Habitat and Logistics module. That's being built by Northrop Grumman and their Italian partner, Thales Alenia Space. And then the PPE, or Power and Propulsion Element, is being developed by a company called Maxar, which used to be called Space Systems Loral. Those will be launched together on a Falcon Heavy rocket in a couple of years. This will not be used for Artemis III. The first landing will just be done with an Orion and the HLS, but after that, future missions will use this as a base camp. It will eventually get one of those Canadian robotic arms, which is why they managed to get a seat on Artemis II. And there will be other international partners as well. So a lot of exciting stuff happening right now. And the last 10 minutes I'd like to leave for questions. So if anybody has anything they'd like to ask, feel free. Yeah. Yeah, so the question was a little bit of a description about the difference in philosophies between the SpaceX go fast and break everything philosophy versus NASA's kind of slow and steady approach with SLS development. It's a great question. So we actually talked about this in depth in one of the master's courses that I took. There's advantages and disadvantages to both approaches. So SpaceX can go a lot faster with their approach than some of their competitors, and that's enabled them to do a lot of really cool stuff. They actually just landed their 200th booster last week, so that was pretty exciting. But it's also a more risky approach, and it's also more hardware intensive. So you can see, for example, the Starship launch that happened back in April didn't work. They had to blow up the vehicle. And so if they had done that with SLS, that would have been a huge loss to the program. SpaceX's philosophy is that they iterate slowly, and so the vehicle that launched in April for the Starship test flight was not a fully realized vehicle. It didn't have a life support system. It didn't have a lot of the other key systems. It was kind of testing out pieces of it at a time. And so that works for their process because they don't mind just, okay, let's just pull out the next one and try it again, right? But they're not a taxpayer-funded organization. They are a private company. They don't report their financials. We don't know what's going on with that. And so they just have that different philosophy, which is working out well for them. For Artemis, NASA chose a very deliberate and careful approach, and that is honed by decades of experience with human spaceflight. In particular, when I was there, Columbia and Challenger were always on the mind and never far from discussion. And so when we're putting together a new human-rated system like this, it involves being really careful and making sure that you test everything out carefully first. And that's why it made sense for SLS to put together a lot of existing human-rated flight hardware. Another thing to remember is that when SLS was initially conceived back in 2011, the Falcon 9 had not yet flown. So that sort of go-fast approach hadn't been proven yet when this was originally put together. And so this was a matter of we need to make sure we have a guaranteed national solution that will work for NASA that involves a number of companies. We're not just dependent on one entity. And so that was the philosophy behind it. I think there's room for both approaches in the industry, and we've seen that there's been a lot of benefit to following either one. Yes, Artemis has taken longer to put together overall, but the result was that Artemis I was a flawless mission. Everything went perfectly. There were no problems. It performed exactly as expected. I think they said the boosters were within like less than 1% of their planned performance. So, you get results from that, even though it's frustrating and it takes a long time. There's a running joke that the tagline that NASA used for Artemis was "We are going." And when SLS kept getting delayed during the flight campaign, people kept saying, "We are going eventually." So yeah, that's kind of my take on that. But you'll get a different answer from different industry professionals depending on their experience and what they've worked with. Yeah.
When do you expect to land that from the Chinese?
Great question. So the question was, when is the expected Artemis III moon landing, and will it be before the Chinese? So right now, the date has moved a few times. Originally, it was 2024 was the stated date. My personal belief is that they picked that date because that was an election year, not really because of technical reasons. And so I suspect it will probably be 25 or 26. Right now, the driving factor for that will not be SLS or Orion, because those are already proven systems, but it will be the lander. Which for Artemis III will be the SpaceX version, because they got the first contract. The Blue Origin one won't be used until later missions. And so they have to prove that that system will work. And so right now that is dependent on that vehicle that in April had to be destroyed by the range safety officer. So we need to make sure that they can follow through on finishing that development process and getting a reliable system that's working. The other piece of that puzzle that's kind of interesting is that getting that large HLS lander to the moon requires a number of supplemental launches that are tanker flights that will refuel that lander in low Earth orbit. And on-orbit refueling of that magnitude has never been attempted before. So I am optimistic that it will work, but that's kind of the driving factor to making sure that we land on the moon on time. As for the Chinese program, the Chinese space program is moving very quickly and very aggressively. They actually just announced some more details about it. They're saying that they are planning to put people on the moon before 2030 using a new rocket that they're developing called the Changzheng 10 or Long March 10, as well as their own proprietary lander and their own capsule and all this stuff. And they're not waiting. They're not messing around. Ultimately, though, I think this is a good thing for NASA, because the reason why Apollo got the urgency was because we had to beat the Soviets to the moon. And so now that we have a pacing challenge again with the Chinese space program, I think that will continue to give Artemis the budgetary support and the urgency that it needs. And technologically, we are still far ahead of the Chinese space program. SLS, is already working. The equivalent Chinese rocket has not even been built. It's probably still, years away. So I think we can get there before them, but, we don't need to sit around. So I'm kind of glad that we have something that's kind of giving us a kick in the pants. Yeah. Personally, yeah, so what am I working on now? I'm personally working on a U.S. Space Force program at the moment, and that's been a great experience for the last few years. Eventually, I'd like to, get back onto an exploration program at some point, but we'll see how that goes. Yeah.
About the new SRBs, there are more segments that increase the thrust rate.
Good question. I believe it might be both. I know it increases the thrust. The question was the extra segment on the SRBs, does that increase the thrust or the duration? I know that the thrust has gone up significantly over the shuttle solid rocket booster. I think the overall duration is about the same because it's about 2 minutes. Yeah.
So you said the components aren't reusable, but the SRB has more.
Yeah. That's a great question. So the question was, the shuttle SRBs were reusable, and since we're reusing them for SLS, why aren't the SLS SRBs reusable? They theoretically could be. There's no technical reason why they couldn't do that. In practice, though, during the shuttle program, they figured out that it actually cost more to refurbish them for the next flight than it cost to just make a new one. And so it was ultimately a cost-driven decision. There's a lot of people out there that have tried to come up with SLS reusability ideas. Personally, I'm all for it. If they can make that work viably, I think that's great. But right now, the decision was made not to reuse them because of that refurbishment cost. And the reason for that is because they get dumped into salt water, and so you have to do all this corrosion mitigation and all this stuff. So it ends up being a pretty labor-intensive process. Yeah. Yeah, great question. So he asked, NASA was trying to work with nuclear propulsion in the late 60s and early 70s, and is that being discussed now? The answer is yes. So NASA has a new office that was stood up, I think, within the last 5 years at Marshall Space Flight Center. That's the Nuclear Propulsion Office. I mentioned, I'm not sure if I really made this clear. So Artemis is designed to be a permanent, sustainable lunar presence that will eventually lead to Mars missions, kind of like they were trying to do with the earlier program. So we're calling it the Moon to Mars program. And eventually, in order to get people to Mars in a reasonable amount of time, nuclear propulsion is the best option for that still. And so NASA has kind of dusted off some of the old designs, and they're looking at them and going, okay, time to update this. So the answer is yes, it is being worked on. Yeah?
Why does the SLS have different colors of orange on the core tank?
Oh, great question. So the question was, why does the orange vary in color on the core tank? The reason for that is because the initial color of the TPS foam insulation is kind of a buttercream yellow, and then the longer it is outside, the more it darkens. And so it basically just ages over time. It's kind of the opposite of something fading in the sun. And so the reason why it looks a little different here is because the core stage was left out on the test stand at Stennis in Mississippi for more than a year, whereas the LVSA, which is that kind of cone-shaped part above it that's the lighter color, wasn't put on until after that. And so basically it's just differential aging in the sun. Yeah?
Those are some good questions. Where can I see it? Are they NASA generated?
Yeah, so good question. He was asking where did the graphics come from. So this talk will be posted to YouTube as a replay, so you can revisit it if you'd like. But most of the images came from NASA. So if you go to NASA's website, they have an Artemis image gallery that has most of the stuff on there. On this presentation, I did try to note where all the images came from. So if you kind of go through the replay, there's a few of them that came from other sources like ULA or something like that. But there's a lot of high quality graphics up there online of all of this hardware. Yeah.
How are they addressing the environmental impact?
It's a great question. How are they addressing the environmental impact that the program will have? So the good news about SLS is that the core stage, which burns for the longest portion of the mission, that's the 10-minute long burn, is a liquid hydrogen, liquid oxygen rocket. And so the only byproduct is actually water vapor. So it's not putting harmful chemicals into the atmosphere, which is great. The boosters, the SRBs, do have some harmful chemicals, so I think that is a concern in the long term. The flight rate for SLS overall will be fairly low, probably 1 a year. So if we're looking at the overall environmental impact of the space industry, which is something that hasn't been studied in a lot of detail yet, but I think will be increasingly as more and more stuff gets launched, this will be a very small contributor overall to that environmental impact. I think the bigger concern is going to be with all of the launches required to launch these satellite mega constellations that we've been hearing about, particularly because the next generation of these satellite launch vehicles are methane-powered rockets, and so that's going to be putting a lot of methane into the atmosphere, which is a greenhouse gas. So the reason why they did that is multi-fold, and I won't go into all that right now. They have engineering reasons for choosing methane for the rocket, but it's not as efficient as SLS, and it's not as environmentally friendly. In terms of the burning up of components coming back into the atmosphere, I don't know how much of that has been studied. I've had that question myself, and so I'd be curious to see research done on the long-term impact of rocket stages burning up in the atmosphere. Everybody kind of seems to treat it like it's no big deal, but I would imagine that over time that would build up as a problem. Okay, we can take one more question. Yeah?
Are there any improvements in the reentry phase? It looks like it's old school.
Yeah, good question. So the question was, are there any improvements in the reentry phase? It seems like it's fairly old school. In terms of the stages reentering, it's pretty much the same concept as the shuttle. The Orion capsule uses tiles, kind of like the shuttle, I believe. Yeah, I think so. There was a trade study that was done between tiles versus a more traditional ablative shield. The heat shield technology isn't really new on any of this system, and they basically decided, hey, this is working, we're going to keep using this. So there hasn't been a lot of advancement done on that. I think some of the newer commercial vehicles that are being developed have some new ideas on the reentry, but for Artemis, it was really more of a leveraging existing technology as opposed to trying to do some cutting-edge, risky thing. But I'd like to see more new ideas about that going forward. So I think that's all we can take in terms of public questions. I'll stick around for a few minutes if any of you have some follow-up stuff afterwards. But thank you all for coming. I really appreciate you making the trip on a beautiful Saturday.